In this video, we're going to take a look at a couple of applications of second-order differential equations. I hope you will remember from a previous class, maybe a calculus class or a physics class, that we have different ways to describe the way things change. We talk about the change in the position of an object by using the word displacement. In other words, if a particle starts here and moves to here, we say it's been displaced by this distance. We talk about the rate of change in position as the velocity of that object. Up here, I might have said this is the amount of change of position versus the rate of change of position. And we talk about the rate of change in the velocity as acceleration. Position is usually, well, frequently anyway, represented by a function s of t. Since the rate of change of position is velocity, the rate of change of position, is the first derivative of position. And acceleration, since it's the rate of change of velocity, is the first derivative of velocity. But since velocity is itself a derivative, we can call this the second derivative of position. And if we have some knowledge about the relationship between the acceleration of an object and its velocity and its position, then we have information about the second derivative of a function, the first derivative of a function, that same function, and the function. Even if we don't know what the function is, if we know about the relationship between the position function, its velocity function, and its acceleration function, then we have a second-order differential equation. And in this way, we can use differential equations to model quite a few physical applications. We're going to focus on a couple here. In this section, we're going to be looking at mechanical vibrations, meaning physical vibrations, and electrical vibrations. The mechanical vibrations will take the form of spring systems. A spring system is essentially a system of things, including a spring, perhaps mounted on the ceiling, or perhaps mounted sideways on a table, a mass or a weight that's attached to that spring, and some forces. We'll come back to the forces in just a minute. In fact, the weight is one of the forces, but we'll come back to that in a minute. If you start a spring system, or if you have a spring system with no weight on it, that spring will not have uncoiled at all. It'll be in its natural state, its natural relaxed position. If you attach a weight, or if you pull the string down, we're going to say that that's positive motion. So downward is positive, and that means that upwards is negative. In this other system, we would say that to the right, or away from the wall, or away from the anchor, that's positive, and backwards is negative, to the left is negative. We can apply all of the things we're about to discuss to this spring mass system or to this spring mass system. And all of the same rules apply with one exception, and that is that in this case, gravity is going to affect the system differently. If it's on a table, then gravity is essentially neutralized, but gravity is still on. And if it's not on a table, then gravity will also be adding a force in this direction. So that complicates things to a point where a physics student would probably be expected to be able to deal with that, but this is not a physics class. So we're not going to do anything with this system at the moment. We're just going to focus on this system here. Now we have some other sort of notation and vocabulary that we're going to use here. We're going to say that the length of the spring before it's elongated is just L, little l. And we're going to say that the amount of which, or the amount by which the string gets lengthened when the mass is added is big L or capital L. So the length of the spring with the weight is little l plus big L. If you then displace the spring even farther, more accurately, if you displace the end of the spring or the center of the weight, right? The end of the spring with the weight on it now gets pulled down even farther. That's a displacement. And so from here down to its new position, we're going to need a name for that as well. And we're going to call that U. And U is a function of T, because if you imagine pulling this down a little bit, if you pull it down a little bit, in one instant it's moved a certain distance. In the next instant, it's moved an additional distance. In the third instant, it's moved even farther. So how far down it's moved from this position depends on how much time has passed. It's a very short period of time, but it's not instantaneous. So it's a function of time. And if you think about it, you could start pulling slowly and then speed up your pull and then slow it down again. So a function of time is appropriate because we can take its derivative and talk about velocity, and its second derivative and talk about acceleration. Okay, now let's talk about the mass, or talk about the forces a little bit. There are four potential forces at work on this system. One is the weight of the weight. Weight is mass times acceleration due to gravity, and this is a force. Combined, the mass of the object and gravity will have the effect that the spring will be pulled down once the weight's attached to the spring. So the weight is a force. Another force at play here is what we call the spring force. If the spring is in its resting position and you attach a weight to it, which pulls it down, in its resting position, there's no energy stored in it. It's just sitting there. But when you attach a weight to it and pull it down, it naturally wants to pull back up. It doesn't want to be in this position. It wants to be in its resting position. So it tries to return to equilibrium. And so the spring force, according to Hooke's law, is some constant times the length it's had to travel, this capital L, away from its natural resting position. In other words, the amount of energy the spring exerts trying to pull itself back up is directly proportional to the amount of distance it's been pulled down. It wants to return that far. Since it's trying to return, it's trying to pull in the upward direction, we say that that force is negative. The constant K will depend on how heavy or thick and how tight and dense the spring is, exactly how much weight there is in the object that's been attached, how far it's been pulled down. It'll depend on a lot of different things, but it's a constant proportionality. Hooke's law says that the spring force is, which is F sub s, is proportional to the distance it's been pulled away. The amount of force exerted by the spring trying to pull it back into its relaxed position is proportional to the distance it's been pulled out of that position. And that all has to do with this system here. But what if I pull it down even farther? Then Hooke's law is going to need to be modified slightly. I think what I'll do is, well, I'll rewrite it and then I'll move it. Hooke's law would say that the spring force was proportional to the length of displacement, where the length of displacement is not just L, but L plus this extra piece here that I pulled it down. So I'm going to say that's L plus U. L, remember, is a fixed number, fixed for this system. It's dependent on the spring, how heavy it is, how tightly it's coiled, what material it's made of, all sorts of things. It depends on the actual mass in this weight. But whatever those elements are, once they're in the system, they're fixed. And so those numbers are constants. How much I pull the spring down, however, depends on time, right? Even if I only move it down a tiny little bit, it takes me some time to do that. And how much I've pulled it down in the first microsecond versus the second microsecond, those could be different. So this needs to be a function of time. So when I say L plus U, I mean a constant plus a function. We're also going to have a damping force, F sub D. This can be very small, depending on what the actual parameters of the situation are, like air resistance in a small, with a very small weight, with a very small surface, air resistance isn't going to be that much. If you had a big plate here that you were pulling down instead, then air resistance would be larger. If you had this in water, the water resistance would be greater. If you had it in oil, it would be greater still. So it depends on where the system is actually situated as to what the damping force actually is. Now, if you're pulling this thing down yourself, if your hand is on the weight and you're pulling it down, it's going to be in the same medium as the weight is in. So you're going to feel the same resistance. In air, you don't feel much resistance. In water, you would feel a bit more. And in oil, especially in heavy oil, you'd feel that resistance yourself. You'd feel that, right? And what you're feeling is, if you imagine your hand in very heavy oil pulling down on something, pushing against the oil, you're going to feel the oil against the back of your hand, and it's going to be resisting your hand pulling down. And that downward motion of your hand is being met by an upward resistance. So the damping force is operating in the opposite direction of the movement of the thing that's being resisted. The faster you try to pull something through heavy oil, the more resistance you're going to meet. And so we say that the resistance is proportional to the speed of the object being moved. In other words, the resistive force is proportional to the speed of the mass. Well, the speed, just as a reminder, if U of t is essentially the position function of the thing, then U prime of t is the velocity, and the absolute value of velocity is speed. So in your textbook, we actually have du dt is proportional to, I don't think they have it written this way, and I shouldn't use k, because we've used k for something else, is proportional to the speed is proportional to the force of displacement. All right, they don't have it quite written that way, but that's the general idea. In that scenario, we call this kind of damping viscous damping. If I now rewrite this as, I'll call it U prime again, and I'm going to divide both sides by this constant. I don't know what that constant is, so when I divide by it, I'll get 1 over c. And I'm going to call that 1 over c value gamma. And that's purely because that's what your book has used for this notation. Again, though, it's going to be negative. I should put a negative here as well. It's negative because it's, as I said a minute ago, it's moving in opposition to the motion of the object. So as you pull the weight down, the force is pushing back up. So now I have a way to write the damping force. It's negative some constant times U prime of t. Okay, I'm going to erase a little bit of this stuff here. In fact, let me do that first. And then I want to just make a quick point, a reminder here, that we know a function, we know a position function, its derivative is velocity. The magnitude of velocity is speed. If you make velocity positive, we call that speed. And if you take the second derivative of that function, I have the wrong pen there. The second derivative of a position function is acceleration. And we have Newton's second law, or Newton's law of motion, which many of you will be familiar with if you've taken any physics, or if you've taken I'm having trouble writing the letter M here. If you've taken calculus, where do we meet that? I think we must learn it in Calc 2 because we do integration. We might even learn it in Calc 1. So hopefully you've seen this. This is not the place to go into detail, but force equals mass times acceleration. So what I'm going to do now is take this version of this equation and rewrite it using the information that we have just developed. So in fact, first what I'm going to do is rewrite it so that the mass times acceleration is on the left-hand side, ma equals force. And then we have mass times acceleration, but we know acceleration is u double prime. Again, remember that this is a function of t. Here I have u double prime of t. I'm just not writing the of t part because I want to save some space. And that's equal to force. But force, there are several forces here. So what it really is a combination of all the combined forces that are potentially working on this system. We have weight. Weight equals mass times gravity, acceleration due to gravity. We have a spring force. We have a damping force. And we have potential external forces, which we haven't actually talked about yet, but there's potential for even more forces than just the spring force and the damping force. The external forces could be something like, your spring is hanging from the ceiling, but the ceiling is outside and there's a wind blowing. So there's the force of wind blowing against the mass as well, which would obviously change the dynamic of the system. If the system is hanging in water and a boat goes by, then the waves created by the boat are going to push the weight around, and so that would change. That external force would change this equation, right? Now, your textbook doesn't use a subscript on this, but I feel like all the others have subscripts. It's a little bit confusing, so I've included the subscript E here. So this is a spring force, this is a damping force, this is an external force. All right, and then we know some other things. For example, we know weight is mass times acceleration due to gravity. We know that the spring force, where's my pointer? The spring force can be written as minus KL, so we'll do that, minus KL, where we know L is the amount of elongation, and K is a constant. And we know how, we have another way to write the damping force as well. It's negative gamma times U prime. And then I'll just leave this one as F sub E. And then one other modification that we can make here, and in fact, the minus KL term in this equation as it's currently written is inaccurate. So I'm going to erase the L, and I'm going to replace that with, if my pen will cooperate, here we go. I'm going to replace that with U plus L. Let me spread that out a little bit so it's easier to read. Because remember that, there we go. Remember that our the L that we had there, right? The spring constant is a constant. Sorry, the spring force is a constant times the amount of elongation. But if we increase the elongation by pulling the spring down, if we pull the weight down, bring the spring along with it, then we've increased the elongation by U, however temporarily. And this U is a function of t. This L is a constant, but U is a function of t. So I've increased the elongation by U. You could write L plus U instead, but for algebraic reasons, I'm using U plus L. If I now distribute, I get mass times acceleration due to gravity minus K. Actually, I will write it as minus KL. And then minus K times the function U minus a different constant times U prime plus any external forces. Now, this pair of terms, as it turns out, is going to equal 0. So that's going to cancel. And the reason for that is that the weight, which is mass times gravity, and KL, which is the spring force, the weight is the thing that adds this elongation. This is the spring in its relaxed form, in its natural state, right? This is the spring in its elongated state. The spring force, once you do that, the spring force is going to try and pull that back up again. And that means that the combination of weight and spring force is equal to 0. They counteract each other. You add those two things together, you get 0. But weight is mass times acceleration due to gravity, and spring force is K times L. So this combination of terms here is equal to 0. And so this combination of terms is equal to 0. So now I have m, mass times acceleration, is equal to negative ku plus gamma u prime plus external forces. I'm going to add, this is 0, I'm going to add these two terms to both sides, and that gives me the equation mu double prime minus gamma u prime minus ku equals f sub e, and voila, we have a second order linear non-homogeneous differential equation. Of course, if there are no external forces, then it's a homogeneous equation. But there's also potential for there to be external forces. So we need to consider the possibility that this is a non-homogeneous equation. But this equation is our goal for this section. This is the thing we're going to be working with, although there is still a bit of work to do before we can dive into any examples. We need to consider the possibility that the system is undamped. If that's the case, then this term will be 0. We're also going to assume for now that there's no external force, so we're going to be working with homogeneous differential equations. So because this video is already over 20 minutes long, I'm going to stop and I'm going to make a separate video for the undamped system, a separate video again for the damped system, and then lastly in this section we're going to be looking at electrical circuits, and I'll do a separate video for that one as well. So look for another video coming right after this one that has to do with undamped systems.